Hello. In this video, I'm going to talk about topics from the second part of chapter 13.5 and 13.6 on equilibrium calculations. This is really the central part of this unit because it really shows the direct application of the equilibrium constants in terms of calculating equilibrium constants or equilibrium concentrations. In all of these problems, we begin with a balanced equation representing a chemical equilibrium. Now, I've divided these types of problems into two categories: the easier types and the harder types. Neither one is really that difficult, but what you are trying to solve differs in the two, and it's important to know what it is you're trying to solve. So, in the easier problems, you are given initial concentrations and some information about equilibrium concentrations, and your goal is to calculate all of the equilibrium concentrations and then calculate the numerical value of K by plugging those into the K expression. How are we going to do this? Stoichiometry, not that hard. The harder problems, you're given all of the initial concentrations of reactants and or products and the numerical value of K, and your goal is to calculate all of the equilibrium concentrations. And our method is algebra. So I simply want to go through in this video and systematically do examples of each of these types of problems to show you the variety of different types of problems you will approach. And you will see that for each of these, there is a very distinct and explicit set of steps, and if you follow the steps, you will get the right answer. So here's an example of an easier problem. We can have phosphorus trichloride and phosphorus pentachloride. After it reaches equilibrium, we see that there is a certain amount of chlorine in the flask. There is the balanced equation, and our goal is to calculate the equilibrium concentrations of everything and then the value of K. So you can see this is what I described as one of the easier types of problems. So what we're going to do is begin by listing the initial concentrations of what we are given. Now, we are given moles of phosphorus trichloride and phosphorus pentachloride in a 1 liter flask, so dividing moles by volume gives us molarities. So I'm going to list phosphorus pentachloride, phosphorus trichloride, and chlorine. And I'm going to list in this table in the first column under I the initial concentrations. 8.70 times 10 to the negative third, 0.298. If no initial moles of chlorine are specified, we should assume that that means there are 0. Okay? I am then going to, over here, in the second column, list the change in concentration that occurs on reaching equilibrium. And then finally, in the third column, I'm going to list the equilibrium concentrations. Okay? This is sometimes called an ICE table for initial change in equilibrium. And you can use ICE tables for both types of problems. Here, we're simply using it as an aid for stoichiometry. Now, we are told that at equilibrium, we have 2.00 times 10 to the negative third moles of chlorine. So I'll put 2.00 times 10 to the negative third as my equilibrium concentration of chlorine. Now, in order to calculate the equilibrium concentrations of the other components, we need to essentially do stoichiometry to figure out what the change is. Well, this is a particularly easy problem because, as you see, the coefficients are all 1. So the increase in concentration of chlorine, which is 2.00 times 10 to the negative third, must be equal to the decrease in concentration of both phosphorus pentachloride and of phosphorus trichloride. Were they not 1-to-1 to 1 mole ratios, you would simply use mole ratios. This gives me now 6.0 times 10 to the negative third moles per liter as my equilibrium concentration of phosphorus pentachloride. This gives me 0.300 molar as my equilibrium concentration of phosphorus trichloride. And this obviously gives me 2.00 times 10 to the negative third molar as my equilibrium concentration of chlorine. So we will then simply take these equilibrium concentrations and plug them into the K expression. Oops. K is equal to the concentration of phosphorus trichloride times the concentration of Cl2 divided by the concentration of phosphorus pentachloride, 0.300 times 2.00 times 10 to the negative third, divided by 6.70 times 10 to the negative third, or 0.0896 as our value of K. Okay, so Again, we were given some information about equilibrium concentrations, and we use that to calculate all equilibrium concentrations, and from that, K. Let's see another type of problem like this. Here is the ammonia synthesis reaction. We are starting with a specified amount of nitrogen and hydrogen. At equilibrium, we find the total pressure in the flask. Calculate the value of Kp. Well, let's begin by writing out the Kp expression. So we know we're going to need to calculate the partial pressure of ammonia and the partial pressure of nitrogen and the partial pressure of hydrogen. Okay. I don't know about you, I'm getting a little sick of the ammonia synthesis reaction. It is literally done to death. Let's set up our ice table. N2, H2, NH3, and we can do this in partial pressures. 0.65 atmospheres of nitrogen, 1.08 atmospheres of hydrogen, 0 atmospheres of ammonia. I should step back and say that one of the things that you normally do in a problem like this is to begin by calculating Q, the reaction coefficient, so you know in which direction it must shift in order to achieve equilibrium. In each of these two problems, we've had none of a product, so we know it has to shift in the forward direction. So here I'm going to define my change in partial pressure of nitrogen as minus x, my change in partial pressure of hydrogen as minus 3x, and my change in partial pressure of ammonia plus 2x. Where do the coefficients 1, 3, and 2 for nitrogen, hydrogen, and ammonia come from? Obviously, they come from the stoichiometric coefficients, okay? Because the decrease in the decrease in partial pressure of hydrogen must be 3 times as great as the decrease in partial pressure of nitrogen, and so forth. So now for my equilibrium partial pressures, I can write expressions in terms of this unknown x, 0.65 minus x, 1.08 minus 3x, and 2x. Okay? Now, I'm not given any of the equilibrium partial pressures of any of these components, but I am told, what am I told? What the total pressure is. What does Dalton's law of partial pressures tell us about the total pressure? Why, of course, it's equal to the sum of the partial pressures. So I can solve for x by simply writing out Dalton's law of partial pressures, which is the total pressure equals the pressure of nitrogen plus the pressure of hydrogen plus the pressure of ammonia. Okay, so 1.09, I'm going to leave out units momentarily, but I'll put them on at the end, is equal to, and now for each of these partial pressures, I'm simply going to take the expression in the E column. 0.65 minus x plus 1.08 minus 3x plus 2x. This is equal to 1.73 minus 2x, or x equals 1.73 minus 1.09 divided by 2, or 0.32 atmospheres. Okay? Now I can use this to go back and calculate from the E column my equilibrium partial pressures. So minus 0.32 equals 0.33 atmospheres of nitrogen. 1.08 minus 3 times 0.32 equals 0.12 atmospheres of hydrogen. And 2 times 0.32 equals 0.64 atmospheres of ammonia. So I'm going to draw a box around my equilibrium partial pressures of all these components. And now, having determined those, I can go back up and I can plug those into the Kp expression. The partial pressure of ammonia is 0.64 quantity squared divided by the partial pressure of nitrogen, 0.33, times the partial pressure of hydrogen, 0.12 cubed, gives me a value of 720 for Kp. Okay? So again, in each of these problems, you are given initial conditions, you are given some information about what occurs at equilibrium, and you're using that information via stoichiometry to calculate the equilibrium concentrations or partial pressures of everything, and from that, calculating the value of K. You know, I think I'm going to stop here and split this up into 2 videos so that the videos aren't too long, and in the next video, I will talk about how we solve the harder problems. See you then.